if you're getting ready for a circuits test, you know that the professor is going to try to put some problems on the test that look incredibly complicated, but there's something simplifying about them. All right, so I came up with the weirdest examples I could think of, just starting with this little mini one for a second. Why would you ever press that switch? What happens if you do? It's called a short. You would short past the resistor. If this is a light bulb, the light bulb would go out. But more than that, you would then be draining the battery as fast as the battery can possibly drain. The battery and the wire would get hot. Drain it in a matter of seconds. So that's a stupid thing, but they could put it as an example. If you connect wire completely across something, you wouldn't go through it. You've shorted the component out. Now for more examples. Okay, physics problems lightning round for circuits. 100 plus 100 plus 100 plus 100 ohms, all in series. That's 400 ohms. 60 and 60 in parallel, that's 30. 60, 60, 60 in parallel, that's 20. 30 and 20 is 50. How did I do that so fast? In series, they just add. And if there's n of them, you just multiply by n. In parallel, if they are all the same, then you can just divide by how many there are. 60 divided by 3 is 20. 60 divided by 2 is 30. So you don't have to go through the whole 1 over r plus 1 over r plus 1 over r. When they are all the same, as often happens on tests, that's a shortcut. 60, 60, 60, they're all the same, so 20. 120, 120, 120. Capacitors in series add upside down, you just end up with 1/3, you end up 40. Batteries. Here's something people get a little confused on. 1.5, 1.5, 1.5. So long as they're all facing the right way, all lined up, they just add. That's 4.5 volts equals I times 45 ohms. So the current's 0.1 amps. What about this situation? This is a weird one. Why would you want to do this? You mostly don't, because if there's any imbalance in these batteries, one of them's going to be busy charging the other one up. But suppose they're both exactly 9 volts. How many volts are across the 72? Do we add them upside down? No. Do we add them? No. It's just 9 volts. The job of this battery is to make sure that this piece of metal is 9 volts higher than this piece of metal. And this piece of metal goes all the way here, and this piece of metal goes all the way here. Each of those batteries has the same job to make sure there's a 9 volt difference. So the voltage across the 72 is 9 volts. V equals IR. It's 9 volts equals I times 72 ohms. So I is 1/8 of an amp, 0.125. Those are a few examples of things that can speed up your circuit analysis on a test. You want to find the shortcuts there. If you have a bunch of identical ones, take advantage. You don't have to do it out the slow way. Here are some more weird examples. Suppose you have a 12 volt battery, 100 ohms here, 60 ohms here. What's the equivalent resistance of this circuit? 100. Why would you ever go through the 60 ohm resistor? It's shorted out. There is a wire going through there. If an electron has a choice of I'm going to run through here or I'm going to run through there, it's going to take the wire every time. That 60 ohm is useless. It might as well not be there. So it's 12 volts, 100 ohms, and the current is 0.12 amps. Now this situation. You have a resistor here, a resistor going up here, and then it just stops. That might as well not be there. It's not a circuit. It has to complete a loop for it to do anything. That's just a dead end. You're not going to pile up electrons there. There's no capacitor plate. So it's just nothing. You can pretend it isn't even there. And this 40 and this 40 are in series. Usually I say things are in series if there's no junctions in between them. Well, even though this is a junction, it's a dead end junction, so it doesn't count. All right, what about this situation? You've got an EMF, you've got resistor 1, capacitance 1, resistor 2, capacitor 2. Okay, what's a shortcut about this circuit? Here's the key thing. When you close this switch, you are connecting this voltage directly to R1, and directly to C1, and directly to R2, and directly to C2. It's like 4 tiny problems. You can just solve that and ignore the rest of the circuit. Solve this, ignore the rest of the circuit. Solve this, ignore the rest. Solve this, ignore the rest. You can just take, if you want to know the current running through R2, there's your loop. V equals IR, done. What about this situation? It's kind of the same thing. You can basically treat this as one loop and treat this as another loop. And the only thing they have in common is the battery is the same power supply. So unless the battery is going to run out, it totally doesn't matter. You can treat it as 2 completely separate problems. The only time you would need to combine would be if they ask, oh, how much current is running here? Or how much current is running here? Because you work out the current for this lap and the current for this lap and add them up, and that would be the current in this wire. Or if you're trying to do this, you'd say, all right, how many currents do I have? Once this thing is stabilized, you wait a long time. The capacitors are full, they're not doing any current. So you've got current there and current there. So this would just be the current through the R2. One more wacky example. So suppose they give you this for a mess, trying to scare you, fake you out. Just look for the junctions. Where do these things connect? There's a junction here, 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 and here, and here. Now, there's an interesting thing over here. This R6 and R7, why would you ever go through them? They might as well not be there. It's a waste of space. It's a decoration. It's a red herring. You would never go through R6 and R7 if you could just go through that wire. It is shorted out. Okay, so now, what do we have? Look for things in series. If they're all on the same band, start from one junction and go along any wire, and until you get to the next junction, everything you hit is in series. So R8, R9, R10, and R11 are all in series. So you might as well replace it with 1. R1 and R2 are in series. Once you have that, you have a much simpler situation. Let's draw it a little less spastically here. So if this is R4, R3, R1 and 2 combined, R8, 9, 10, 11 combined, and this is R5, well, that's a much more reasonable looking circuit, right? These guys are in parallel, these guys are in parallel. Combine them, and then you just have 3 in series, and you've got it. Look for dead pieces of circuit. If there is a wire cutting across the thing entirely, then there's no reason why it would fight its way through resistance. Now let's apply these things. Here's one big example, and yet we can do it quickly. The capacitance. 1, 2, 3, 4, all identical C, so they're just going to add up. 210 times 4 is 840 microfarads. And then you've got 210 and 210. So now you've got even the 210 and the 210, you could combine to make half of 210, 105. So you can have 1 over 105 plus 1 over 840, and you've got a much shorter equivalent capacitance problem to work. 840 over 9, whatever that works out to be, that's the CEQ in microfarads. Now the resistance. Each resistor is 60. 60, 60, 60 is 20. 60 and 20 is 80. 80. The REQ is 80 ohms. You don't have to go through the whole calculation because they're all identical. So what's the time constant of this circuit? The time constant is the R equivalent times the C equivalent microfarads. So whatever that works out to be, there's your time constant. One last trick. Look at the batteries. How many volts do we have? We don't have 6 because that battery is plugged in backwards. 1.5, 1.5 minus 1.5 plus 1.5, you've only got 3 volts. So watch out for that. They might put a battery in backwards just to try to mess with you. I hope you found those helpful.